Welcome to Chapter 2, where we focus exclusively on supercritical carbon dioxide, often abbreviated as SCCO2 or supercritical CO2. This chapter explores why carbon dioxide has become the green solvent of choice for industries ranging from food processing to pharmaceuticals. With its accessible critical conditions, exceptional safety profile, and tunable properties, supercritical CO2 represents one of the most important tools in the green chemistry toolkit. Let's explore what makes this molecule so special in its supercritical state. The critical parameters of carbon dioxide are remarkably accessible. The critical temperature is 31.1 degrees Celsius, just slightly above room temperature. This means you can work with heat-sensitive biological compounds without risk of thermal degradation. The critical pressure is 7.38 megapascals, equivalent to about 73 atmospheres. While this sounds high, it's easily achievable with standard industrial equipment, no exotic high-pressure technology required. The critical density is about half that of liquid water. These parameters explain why CO2 dominates industrial supercritical applications. Understanding the relationship between pressure, density, and solvent power is key to using supercritical CO2 effectively. As you increase pressure above the critical pressure, the density of CO2 rises dramatically. This density increase directly correlates with enhanced dissolving power. At low densities of around 0.2 to 0.4 grams per cubic centimeter, achieved at moderate pressures, CO2 preferentially dissolves light, volatile compounds like terpenes and aromatics. At medium densities, it captures essential oils and flavonoids. At high densities approaching 1 gram per cubic centimeter, it can dissolve heavier compounds like lipids and waxes. This pressure-tunable selectivity is a major advantage. There's one important limitation to understand. Carbon dioxide is a nonpolar molecule. Looking at its linear structure, the carbon-oxygen bonds do have polarity, but the symmetrical arrangement means the dipole moments cancel out completely. The result is zero net dipole moment. This makes pure supercritical CO2 an excellent solvent for nonpolar compounds like fats, oils, terpenes, and many alkaloids. However, it struggles with polar molecules like sugars, proteins, amino acids, and ionic compounds. This follows the classic principle that like dissolves like. Fortunately, there's a solution to this limitation, which we'll discuss next. The tunability of supercritical CO2 is one of its greatest strengths. Think of it like having two control dials, temperature and pressure. By adjusting these parameters, you can precisely control the density and therefore the solvent power of the CO2. This enables a technique called fractionated extraction. You start at low pressure to extract the lightest, most volatile compounds first. Then you progressively increase pressure to capture heavier compounds in separate collection vessels. This approach allows you to selectively extract and separate different compound classes from the same raw material, something difficult or impossible with conventional solvents. To overcome the polarity limitation, we can add small amounts of polar co-solvents to the supercritical CO2. Methanol at 5 to 20% is the most common modifier, significantly extending the range of extractable compounds. Ethanol is preferred for food and pharmaceutical applications due to its safety profile. Even small amounts of water, around 1 to 5%, can enhance the extraction of certain polar compounds. The co-solvent molecules provide the dipole-dipole interactions needed to dissolve polar solutes. However, there's a trade-off. Adding co-solvents means you'll need an additional step to remove them from your final product, somewhat diminishing the pure green chemistry benefit. Temperature choice involves interesting trade-offs. At lower temperatures, like 40 degrees Celsius at the same pressure, you get higher CO2 density, which means greater solvent power. This is better for extracting heavier compounds and essential for preserving thermolabile or heat-sensitive materials. At higher temperatures like 80 degrees, density is lower, but you get faster mass transfer due to increased molecular motion. There's also a crossover effect. For some compounds, solubility actually increases with temperature despite lower density, because the compound's vapor pressure increases faster than solvent power decreases. Optimal temperature choice depends on your specific target compound's properties. The safety and environmental benefits of supercritical CO2 are substantial. It's completely non-flammable, eliminating fire and explosion, hazards common with organic solvents like hexane or ethanol. It's non-toxic and carries GRAS status, meaning it's generally recognized as safe by the FDA for food and pharmaceutical use. When you reduce the pressure, CO2 simply becomes a gas and evaporates completely, leaving zero residue in your product. This eliminates costly solvent removal and testing steps. The CO2 can be recovered at 95% or higher efficiency and recycled back into the process. And it replaces truly hazardous solvents like hexane and dichloromethane from industrial processes. Let's compare supercritical CO2 directly with conventional organic solvents. For residue in product, CO2 leaves none, while organic solvents require careful removal to meet parts per million regulatory limits. For flammability, CO2 is inherently safe, unlike most organic solvents. CO2 has zero toxicity, while others pose various health hazards. The selectivity of CO2 is tunable through pressure and temperature, while conventional solvents have fixed selectivity. For separation, simply reducing pressure releases CO2, while other solvents require energy-intensive distillation. CO2 has full GRAS status versus regulated usage for organic solvents, and the environmental impact of CO2 is far lower than that of volatile organic compounds. To summarize Chapter 2, supercritical CO2 has an accessible critical point at just 31 degrees Celsius and 7.4 megapascals. As a nonpolar solvent, it's naturally suited for lipophilic compounds, but this range can be extended with co-solvents. Properties are fully tunable by adjusting pressure and temperature. Adding 5 to 20% methanol or ethanol enables extraction of moderately polar compounds. And CO2 is truly a green chemistry champion, non-toxic, leaving no residue and fully recyclable. In Chapter 3, we'll explore the opposite extreme, supercritical water, which operates under far more severe conditions, but offers unique capabilities for waste destruction.